Good morning, it's Paul with the introductory video for Class 18 of Math 117. The topic for today is martingales, which will figure prominently in the entire rest of the course. The term martingale originally arose in the context of roulette, and you may actually have heard of the martingale system for playing roulette. Here's how it works. You pick some bet where you have a 50% chance of winning. This requires finding a roulette wheel that doesn't have a 0 on it. Good luck. But say you bet on red, and since there are 18 red numbers and 18 black numbers, you have a 50% chance of having your bet of 1 turn into 2. You have a 50% chance of losing 1 chip and having your 1 turn into 0. Okay, if you win, you've gained a chip. Otherwise, you're down 1 chip. What do? Well, you bet 2 chips on red the next time round. If you win, you will gain 2, and your net gain for the 2 spins of the roulette wheel will be 1. Otherwise, you're down 3. So what do? You bet 4, and you will either win or lose. If you win, you gain 4, and you're up 1 chip for the sequence of 3 spins of the wheel. Otherwise, you're down 7, no problem. You will bet 8 the next time around. And the theory of this is sooner or later you're going to win, and so you have a guaranteed gain of 1 chip. The problem is you need an infinite bankroll in order for this system to work, and it turns out that the probability that you will exhaust your funds is bigger and bigger as you go to more and more rolls. And if you set out, say, to win $1 million using this system by playing for a long time, and you've only got a couple of $1 million backing you up, you've got a significant probability of going bankrupt before you achieve your goal. Now, there's a mathematical complication with this or any other martingale. In order to have a martingale, we need 4 things. We need a sample space, we need a sigma field, we need a probability measure on that sigma field, and we need a filtration. So think about this roulette martingale. The sample space consists of infinite sequences of coin flips. No guarantee that you will have achieved your goal after a finite number of spins of the roulette wheel or flips of a coin. And the infinite sequences over any set always form an uncountable sample space. That's a bit of a problem. In particular, for an uncountable sample space, we know that we get into trouble if for our sigma field we try to use the power set. That's why we had to introduce the Borel sigma field for the uncountably infinite sample space of real numbers between 0 and 1. It's also tempting to say that our probability measure says every sequence of coin flips is equally likely. But that's true trivially, because the probability of any specific infinite sequence of coin flips is 0. And we don't allow uncountable unions. We can get around this by saying that we're only going to consider events involving the first n coin flips, and that each of those gets an equal probability of 1 over 2 to the nth. F sub n is part of our filtration. It's the sigma field that contains the information about just the first n tosses, but nothing beyond that. And that's a perfectly good finite sigma field. So as long as we focus our attention on just n steps, we can skirt the mathematical difficulties. Now I can define the martingale condition. After n coin flips, or n spins of the roulette wheel, we have a random variable, which I will symbolize by x sub n, and it's adapted to the filtration. That is, each x sub n is constant on each of the events in the sigma field f sub n. And what the martingale condition says is that the expectation of the random variable x plus 1 conditioned on f sub n is equal to x sub n. There's less to this than meets the eye. Let's think of it in terms of coin flips. What it says is that the expectation on day n plus 1, where the coin is flipped for the n plus first time, given what has happened up through day n, is equal to your winnings after day n, for the simple reason that a coin flip is a fair game. If you happen to have $48 after day n, and you're going to flip a coin in such a way that you either win or lose $5 on the next day, your expectation for the next day, conditioned on having $48 on day n, is another $48. Sometimes when you do this, the random variables you choose will generate a sigma field that is actually smaller than your filtration. This happens in a couple of our two-step scratch tickets, where on day 2 there are only 3 possible values for the share, in spite of the fact that there are 4 different sequences of up and down over 2 days. 2 of these have coalesced into 1, and if that happens, you can condition on this smaller sigma field, G sub n. Now let's consider how we might make martingales. Here's the simplest way. We choose a sequence of independent random variables, call them x sub n. They all have expectation 0. Now I can only talk about random variables being independent if they're all functions on the same sample space. So that means my sample space will have to be something like an infinite sequence of coin tosses, and then the 5th of these random variables could be you win a sub $5 if you flip heads on the 5th toss, you lose it if you flip tails. There's no requirement that the payoff has to be the same from day to day, and we can generate our filtration by the various random variables. How do I make a martingale out of this? I just take the sum of the values of the first n random variables. So, for example, if we think about playing roulette with no 0, we need no 0 in order for the game to be fair. Each x sub I could result from any finite allowable bet. x1 could be the gain that you get if you bet 10 chips on even on the first day. x2 could be the gain that you get if you bet 5 on the numbers 1 through 12 inclusive are going to show up, in which case you've only got 1 chance in 3 of winning, but your winnings are equal to double the amount of your bet if you win. x3 could result from betting 1 on a single lucky number, like 13, in which case you will either lose 1 or gain 35. Each of these x sub I can be specified in terms of a single spin of the wheel, but the sample space consists of this uncountable set of infinite sequences of spins. Another way is we've got a random variable x, we have a filtration, and we set the random variable x sub n to be just x conditioned on f sub n. This is exactly what we've been doing with our multi-step scratch tickets. For the Purcell scratch ticket, for example, x0 is the value on day 0, x1 is the value on day 1, x2 is the value on day 2, and we have already been using the Martingale condition over and over again by saying that the value of this scratch ticket on day 1 is equal to the expected value on day 2 after the final scratch. Here's a method that superficially looks exactly the same as the first method. We're going to start out with a sequence of probability spaces, and on each of those probability spaces we want a random variable x whose expectation is 0, and we add together the x sub i's. The only difference here is we have a separate probability space p sub n for each day or each coin flip. And what we have to do is, from these sample spaces, one per day, we have to make a product sample space. Making a product sample space out of 2 coin flips is perfectly easy. Making a product sample space out of an infinite number of coin flips is such a mathematical mess that even though it's discussed in Deneen's book, I decided to leave it out of this course. However, we can solve the problem by worrying only about finite sequences. We can say that one of the events in our filtration is a product of specific events that happen on days 1 through n combined with the entire sample space for all the days that are yet to come, and the probability measure that goes along with this is the probability that event A1 will happen on day 1 times the probability that event A2 will happen on day 2 on up through day n, and then a probability of 1 for the entire sample space subsequently. Once we've done that, we've basically converted method 3 into method 1. Now there's a special case of this method that's very important. We're going to make each x sub n have only the values +1 and -1, and each of these, of course, will have to have probability 1/2 if we're going to have a fair game. This has been around for a long time. It's known as a symmetric random walk, and in fact it plays an important role in the theory of diffusion and Brownian motion in physics. It should be pretty obvious that the sum of these x sub n's, I should have written the sum of x sub I apologize for that, from 1 to n, is going to be a martingale. A surprising result, which we will prove and use later, is that we can make another martingale out of this by taking the square of y sub n and subtracting off n. That quantity, remarkably, has the same expectation every day. As a special case of this idea, what we do is create a random variable which is 1/2 plus the sum of these values from the random walk, only divided by 2 to the n plus 1. Now think about this. We start with 1/2, then we either add or subtract 1/4. For the next value of n, we take that result and either add and subtract 1/8, and then we add and subtract 1/16. What we're basically doing is generating the binary expansion of a real number between 0 and 1, one binary digit at a time. Each value of x is going to be equally likely. That is, the random variable x takes values in the closed interval from 0 to 1, and the probability measure is the same as Lebesgue measure. Now for a brief overview of a difficult topic. We'll be concerned for martingales, which we will be considering in subsequent weeks, whether the sequence of random variables x sub n has a limit, or at least has a limit with the possible exception of events whose combined probability is 0. This is actually proved in Deneen, but we're going to skip over the proof. The answer is this limit exists almost surely if the expectation of the absolute value of x sub n has a finite supremum. You look at this first and say, of course this supremum is going to exist. This is a fair game. The expectation is always 0. But not so simple. You see, it's the absolute value of x sub n we're considering here. It's in fact very easy to create martingales with the property that the expectation, if you consider only positive values, is not bounded. You could, for example, go to your favorite casino, keep betting on even in a fair roulette game. Your expected total winnings are always 0, but if you arrange so that if you win, you get to keep your winnings. If you lose, your debts are forgiven. The expectation of y plus will keep increasing. One way to see that this has to be so is notice that your winnings on successive spins of the wheel are independent events, each with a variance of 1. So the variance of the sum of your winnings after n spins of the wheel is going to be n. The variance goes up, and that means the values that are far away from 1 get more and more frequent. A simple way of making martingales converge is to put a bound on x sub n, and in the case of a symmetric random walk, we can easily do this. If you're actually thinking of someone taking steps randomly right or left, we can say when they get a certain distance from the origin, they hit the wall. If we're doing casino gambling, on the other hand, we can say that suppose the gambler starts with $500. If she goes broke, she has to quit. If she doubles her initial stake by getting up to $1,000, she declares victory and quits. However, there are convergent unbounded martingales, and I'm just going to tell you the result here. If a random variable is integrable, then the probability that its absolute value is very large, greater than some integer m, has to approach 0 as m approaches infinity. Otherwise, the integral won't exist. Deneen actually proves this by using the dominated convergence theorem. If we have a sequence of random variables, we need a requirement that's stronger than just each of these random variables is integrable. Instead, we need the sequence to be uniformly integrable. And uniformly here is used in the same sense as in uniformly convergent or uniformly continuous. That is, we choose the order of the quantifiers as follows. You challenge me by specifying some positive epsilon. And then I have to make the next move. I say, I'm going to choose a nice large value of m, and we're going to compute the probability that the absolute value of the random variable x is greater than the m I've chosen. If this works for any value of I, then I am the winner. This sequence of random variables is uniformly integrable. If, on the other hand, no matter what m I choose, you can always choose an x sub I for which this quantity is greater than epsilon, then each of the individual random variables in the sequence might be integrable, but the sequence itself is not uniformly integrable. Deneen actually proves the key result for convergence of martingales, and if you want to take a graduate level course in this topic, you can prove it too, but not in this course. What the Martingale convergence theorem says is that if we have a martingale that's uniformly integrable, then that martingale converges almost surely to some limit x, and furthermore, that the limit of the expectation of the absolute value of the difference between the limit x and the nth random variable in the sequence is equal to 0. Nice to know this theorem exists, but don't worry about it any further.